So our next speaker is Professor Bruce Watson. Good afternoon, Bruce. And Bruce will share with us what we need to do software that works, I guess. Yeah. Thank you very much, Bruce. You're welcome to start sharing your screen.
Okay. Hey, Francesco. Hi, esteemed colleagues and guests. I'm not actually really nervous. Can everyone hear me? Can you see me, Francesco, and hear me?
Hear you, and we can see you. No, we can't see you, but
okay. I have my camera on, so it should be streaming, and it might be the view setting with the zoom on your side, but you can see the slides at least.
We do. We will fix the video camera while you speak.
Okay, excellent. Yeah, so let me dive right in. It's actually a real honor to be one of the speakers today, but also a real honor to be following the people that have spoken before me. So many of them set the stage for the things that that I will talk about, and in particular, it was very exciting to hear about some of these extremely advanced technology developments. Starting at the beginning of the day, of course, with Dr. SITHOLE Happy's presentation all the way until Heike's immediately before mine. And so what I'm going to talk about now connects with some of that and set a few things in context, some of which are actually somewhat older computational and algorithmic development questions. And as soon as I tell you a little bit about the history, you'll see precisely how old. But some of these things are really topical, remain topical today, and I hope to just highlight a little bit of that and then encourage people to think about that a bit more as well. So I'm going to talk a little bit about the motivation and the need for correct software. I think everyone would find that believable, especially in the high performance and computational physics community. This may be self-evident. I'll give you a little bit of an example, and I'll show you briefly one of the tools that with some collaborators in Braunschweig in Germany and now in Karlsruhe we've been working on, and then I'll close that off and we'll lead to I think the final talk of the day. So one of the things that you know, as I say, is perhaps a little bit self-evident is although we tolerate problems with software on a daily basis, so web browsers that crash or editing tools that crash, our computers as well, our laptops, there are also some very spectacular failures. So there are just a couple of them mentioned here. This is not even discussing the ones that are in the medical space where things are actually even more critical. But these three examples are all scientific and engineering related, and the most spectacular ones tend to be the ones that involve spacecraft. But nonetheless, there have been a bit of a recurring theme. And the idea that software is something that's remarkably difficult to produce is, of course, also well known and has been known for the past 60 years or so. But how to get it correct is something that's also been well known for at least 50 years, but is rather badly practiced, simply because we have other techniques that typically work well enough. But as the price of big science goes up and the exciting things to be discovered grow, it really becomes topical for us to tackle this. So further to the motivation, I would say that it's worth reflecting on the fact, at least from my perspective as an algorithmic nerd, that algorithms are one of the maybe two most important inventions that we have as humans. And good quality algorithmics, whether it's done by a human or by a machine, is of course then key to the quality of the outcomes. It turns out, however, that inventing and developing new algorithms is remarkably difficult. So it's typically done by people who have a real knack for this or real talent for this. And for the rest of us, you know, these are often done just by trial and error, if you will. It also is the fact that there are a ton of algorithms that remain to be invented. Now, of course, that kind of existential comment is very vague. But the fact that we have steady progress in inventing and coming up with new algorithms is reassuring in that regard. It's also worth saying that really only a fraction of algorithmics is correctness critical. However, it remains that these things, for example, in square kilometer array or in CERN and various other big science projects there, it really actually matters. And also in these other safety critical things as well. Then lastly, we have a couple of more modern puzzles, certainly from the last couple of months. Everyone's now been exposed to the fact that we have algorithms making algorithms, so ChatGPT being one of them. But also, as Heike was talking about, moving into quantum computing in the medium to long term means that we have also a need for correctness-based approaches to developing algorithms. So how do we normally check that algorithms are correct? Those of you that have programmed will be accustomed to at least some of these. The vast majority of programmers actually go with what I call the hope and pray method. So they basically have written some code and then they'll try it out and more or less hope that it works, and they'll try it on some data sets. And typically it does work, or works well enough. But of course, the fact that you haven't observed a mistake doesn't mean that there aren't any mistakes present. And with very, very large data, it then becomes problematic to exhaustively test it. And what are you testing it against? So the testing approach is also, to an extent, a bit problematic. There's also verification, very exciting way of tackling it, and lots of expertise. And I would say that of the formal approaches, number 3, the verification approach is by far the most appealing. All of the large companies do that kind of thing. Also for circuits. So you'll see that with Intel and IBM and many other companies as well. And then there's proving stuff after the fact, which is very much an academic exercise, but also is done. Now back to correctness by construction, or CBC. So this is the approach that I advocate for, and I'll briefly mention today and just give you a couple of examples before we run out of time. We tend to start with the notion of a precondition and a postcondition. So this is what will be true before the program or algorithm runs, and what will be true, or what we want to be true after the program is run. So these are called the pre and the post conditions. And then we have a logic and a number of allowable steps that will allow us to manipulate the program and eventually arrive at an algorithm or a program, which is then implementable. And we typically do all of this using a lightweight logic. For those of you that are logic people, it's a first order predicate logic, and we use a kind of pseudocode, although you could use Java or C or C++ or something along those lines. So we have some success with that kind of thing. You could ask yourself, where is CBC, correctness by construction, used? And I would say it's actually used in all kinds of other engineering disciplines. So certainly in civil and mechanical engineering, there's a long history of knowing that the individual components are correct and having specific rules for the composition or the assembly of these components. And we also know that in electronic engineering, the way circuits are built up functions in exactly the same way. The software is notoriously more difficult, mainly because, there are these actions at a distance. So in that sense, it has a resemblance to quantum mechanics. But within the memory of a computer, one software module in one part may have a long distance effect on something else. So the notion of doing correctness by construction is just a little bit more difficult. The industry uptake of this approach is remarkably low, which is a shame. And this is why we advocate for a lightweight approach to this, and why we're specifically working on software support tools so that it's not purely an academic exercise. And the additional thing is it's possible to actually decompose the problem and then farm subparts of the problem out to individual sub-teams. So there's certainly a divide and conquer approach, which is very successful as well. The industrial uptake, however, there are a couple of spectacular success stories, but the investment is non-trivial. You typically need people who've got a bit of experience with this. You need to assemble a team around them, and of course, you need support tools which are not yet in place. But nonetheless, it's well known that in some mechatronics type companies, there have been cases of 10, even 100 times improvement in the quality of the code in terms of bug density, but also in the time to development or time to reach a certain bug density. So this is, I would say, reassuring. Now, personal quotes, those of you that happen to use C++ will recognize the second guy. Only computer scientists will recognize the first guy, but he did win a Turing Award for things related to this. And these gentlemen have specifically pointed to these kind of correctness by construction approaches as being important, and also the specific kinds of software where they're usable. So the people who were involved in this, I'll just zip through this, but it was basically a guy named Floyd and Dijkstra and Tony Hoare in the middle. These guys came up with this stuff already more than, well, not quite 50 years ago, but we are talking about 5 decades ago. And it was publicized initially by Dijkstra with his book, which if you take a look on Amazon, you find all kinds of snarky comments like the one at the bottom. So it's sort of an undervalued field of computing, which is a bit of a shame. And there have been some follow-up books to that as well. So lots to be found online. Many of these books have become available as open source or PDFs that are findable. So how exactly does correctness by construction work? Well, we start out with a specification for our program, and we'd like to build that specification through until we have an executable program. And we do this always with only using correctness preserving transformations. So it's like we do in any other field of mathematics. Moving from one line to the next, you will preserve correctness of what you're doing. And of course, you may have some additional proof obligations, which you need to actually then tackle and pay attention to. Otherwise, the entire thing is not correct. And at the end of it, all of these steps that you've taken, because each of them is correctness preserving, you have an algorithm at the end which is correct by construction. So that's actually good news. The examples I'll give are very short examples. I'll gloss over all of the details, but I just want to illustrate that it exists and give you some pointers to how to do this yourself. We tend, at least in my research group, we tend to focus on imperative programs. If you do functional programming, things actually get much, much easier just because the programming languages are much cleaner. And we also tend to use this relatively simple logic in which we actually know that there are some holes, but nonetheless, they're not of really important impact. So, okay, rather than belaboring that, let me show you the two short examples. And as I said, I'm going to leave out 99% of the steps as I show you these examples, just so that we get this done and also give you a taste of what this is about. So a sorting algorithm, we want to sort an array. We've got an array of, let's say, floating point numbers, and we want to sort this for whatever reason. And we'll start off with a generic looking algorithm like this. And the stuff inside the curly braces is always an assertion, so a statement of fact or a thing that we would like to be true. So that's actually written in our logic. And P is our precondition and Q is our postcondition. And the thing that's sandwiched in between the two is some chunk of program, so some statement or sequence of statements that form the algorithm. And we would like to construct S in such a way that if we start out with P being true, we will at the end be guaranteed that that Q is true, and therefore we've accomplished what we want to do. And in the case of sorting, again, this is a super simple algorithm, and we're not even going to do a fancy sorting algorithm like quicksort or something along those lines. But we would flesh out the pre and post conditions a little bit like the following. And we'd say that we assume that the array is not empty. So that's written in a kind of pseudocode, if you will. And I think most people would find it believable that we'd like the length to be greater than 0. And as our post condition, we'd like the array to be sorted. And there I've magically introduced a word called sorted, but I think we have an intuitive gut feel for what that means, at least for the purpose of this example. I'm a big fan of drawing pictures of these kinds of things. And if we take a look at the array, it will look something like the following. We will, in our particular case, we already know that we will use some kind of index I. So we'll use this index and we'll travel through the array from one side to the other. And as we travel through the array, we'd like everything to the left of the array, excuse me, everything to the left of the array, we'd like to be sorted, and everything to the right of the array is unsorted or possibly unsorted. We actually don't really know. And because we're going to be moving from left to right, it means that we start out having the entire thing unsorted. And by the time we've moved the pointer, the index I from the one side all the way to the other side, we'll then have the entire array being sorted. So we've got a couple of things that we can say about this. Sorry, let me just back up one step. This thing here, the statement that I've just made, intuitively is what we call an invariant. So we know that we're going to need some kind of loop in our program. And as we progress in that loop, there's something that we're going to need to know is always true. And that is that everything to the left of I is sorted and everything to the right of I is stuff that we don't know. There are a few other things that are also part of the invariant. We would like to say that we haven't manipulated or damaged the array, et cetera, but those are sensible conditions. And then we have something called the variant, and this is what we use to argue that the algorithm is correct. And the variant is that chunk of the array to the right, which is just going to be squeezed and squeezed and squeezed until it becomes 0. So that's our monotonically decreasing function, and we would like to introduce that so that we can argue that this algorithm will eventually end, because the termination of algorithms is one of the notoriously difficult things as well. Now, we could have done this also fully in the predicate logic, and that's actually what we do when we write this out. Although nowadays, instead of doing this in LaTeX, we would typically do this in our tool that I'll show you in a moment. But what's captured at the bottom there, the invariant with a capital I, basically says what I just said, that everything to the left is sorted, and we're not saying anything about what's to the right. And then we can write it out in a little bit more detail as well. Now, armed with that, we can then go and do our first refinement. I'm going to skip over this step as well, but I can assure you that after only 3 refinement steps, and each of these refinement steps is what I previously called a correctness preserving step. After each of those, we will have a correct algorithm, but it may not be an implementable algorithm. So we'd like to continue the sequence of steps until we've arrived at something that we know that we can implement. And implement means type it in C, C++, Java, Pascal, Fortran, or whatever. And here we are at an algorithm which has an outer loop, which is iterating I from left to right, as we previously agreed. And then there's going to be some statement on the inside, which actually needs to ensure that this invariant remains true, even as our index I marches from one side to the other side. So there's still a statement S3 that you'll see in the middle of the screen there, which is still to be fleshed out. But that would be a statement that would maybe manipulate the item in the array, the floating point number at index I, and it would maybe puzzle out whether it needs to fit in somewhere else in the array, or it may bubble it further down the array. And in doing that, we'd wind up with some of the well-known sorting algorithms like bubble sort and so on. So I'm not going to talk that through any further. I'm going to briefly show you a transitive closure one, and also how this proceeds. This is arguably one of the simplest possible graph algorithms that you can come up with, graph problems and graph algorithms. But transitive closure, I think many of you that are familiar with graphs will know this concept. And in this case, we have our very simple graphs where each node has only one out edge. And for example, the transitive closure from node 4 would then capture not just 4, but also 6, 7, and so on. And then also the loop back to 5 would be caught. And an algorithm would be able to follow each of the links and then collect the various items in the transitive closure. But we'd also like to do some bookkeeping to make sure that once we've found things that we've previously seen, we don't need to then go and exhaustively do them again. So we can formalize that with the stuff that's in the bottom left corner. And we can then go to making up our algorithm. And the algorithm has a longer looking precondition, but it's basically just saying that we have some finite set. And also we have some function, which is simply expressing our single edge graph structure. And we have some starting node. And what we would like to do with statement S is come up with an algorithm that then computes for us a set D, which is the set of done nodes, which is then the transitive closure of node 0. And after a whole bunch of steps with introducing an invariant, we would eventually arrive at an algorithm that looks a bit like this, with a couple more steps to be filled in. So rather than doing the tedious way of doing that, the final algorithm looks like this. And this is a well-known bookkeeping type algorithm where we've got a set done and a set to do. And we simply march through the graph until we've run into things that we've previously run into. So I think most people would intuitively come up with this algorithm, even if they don't come up with the correctness argument. Now, rather than forcing people to actually go and do all of this in LaTeX, which is, as I say, extremely tedious and very painful, although it is something that I've done quite a bit, we have some tool support, and this is actually thanks to the group that was in Braunschweig that's now partially in Karlsruhe. And this has been a very successful collaboration in building out this tool. It's an Eclipse plugin. It's available, so you can find the URL at the bottom, or you can, of course, email me for that. But what it supports is a graphical way of then elaborating on the nodes. So starting at the top of the algorithm, you fill in the precondition and the postcondition, and you have some abstract statement, and then you have a palette of different possible correctness preserving moves that you can apply. And this is exactly how we do it intuitively when we do it purely with pencil and paper. We know what these possible moves are, and here we've simply codified it. And of course, if there are more elaborate moves or changes of programming language that are done in the future, that would be easily adapted into the tool as well. So Quark is the tool, so the correctness by construction support tool. It provides then for this tree-based structure. It provides an additional thing which I haven't elaborated in this talk, but we can come back to. If any of you are interested, I can email you about that. But it allows for also the elaboration of taxonomies. And this is important because there aren't always just one algorithm interestingly solving a problem. Many of them may be suitable depending on the particular characteristics of the problem. So there's a whole field of parameterized algorithm exploration. And we'd like to be able to support that. And these can be arrived at by allowing for one possible choice that leads down that branch and to one family of algorithms, and another choice that leads down a different branch to a completely different family of algorithms. So it's encouraging to be able to support that directly in a tool like this that then embodies all of the correctness arguments, but also highlights for us where the commonalities are of the algorithms and where the divergence points of the algorithms are. We have been able to connect, and this is actually done from the beginning, excuse me, connect Quark directly to a verification tool. So many of you will use verification tools for mathematics, of course, but also for program analysis. And Key is one of the verification tools. Key rather specifically supports Java. It may actually support a number of other things now as well, but it's was at least a little bit Java specific. And that means that, you know, piping things from our CBC support tool through to Key was a very easy win, and that allowed us then to do the verification steps. And I mentioned verification steps not because we're trying to sneak in this approach of verification through the back door, but because of each use of a correctness preserving transformation in deriving the algorithm, you typically have some small number of correctness proof obligations that arise. So you need to prove that this implies this. And these are usually fairly straightforward and the kinds of things that you can outsource to a student. But if they can be automated and done in a fully provable and automatable fashion, that's all the better as well. So Quark provides support for that. One of the interesting things that arises out of this is developing algorithms through this pipeline as opposed to purely using Quark, which is actually a long-standing standard tool for proving some aspects of Java programs correct. Arriving at algorithms our way versus going and taking your algorithm that you've cooked up by pure talent and putting that through Key. There are some interesting differences. So the total amount of effort going into proving and the number of proof obligations does turn out to be a little bit better using our approach, or perhaps the same in some cases. And the verification time is also considerably better in some interesting cases. And I say some interesting cases because you can see here the one pattern matching with the largest difference. That arises really because we we know that this is a significantly complicated problem as opposed to exponentiation and factorial and some of the others that are rather more toy problems. I'm going to skip over these. I'm happy to come back to them, and I'm going to go straight to the conclusions just based on the time. And I hope I've been able to give you a sense of the significance of there being an approach to correctness by construction. So the traditional thing of throwing our hands in the air and saying, well, you know, there's no way all software will be correct. That's one approach that many people take. Or the other approach is, like any programmer, I also am somewhat charmed with the code that I write. And I meet many programmers who are very confident in what they've done, and rightfully so, because especially in big science, many of the people coding these things are very, very clever. But nonetheless, we can all make mistakes, and the implications of making mistakes if you're doing something like processing part of the square kilometer array pipeline or CERN or something else, it means that not all of the data will be cached or not easily retrievable. And we can get considerably far through the data before we actually realize there's a problem. So I think there's a sufficient motivation for us to take these approaches as one of the things that we should do, certainly for the core of the computation. And there's quite a bit of future work, so there's no shortage of interesting things that we're working on. Just to tie things into the last couple of speakers, it was very interesting to see both IBM and Intel before just speak of the specific interesting problems that arise. And we happen to be working also on correctness by construction for quantum computing. And this involves coming up with appropriate logics that then support that. So we could have correctness arguments attached to Qiskit programs. And we're also working, and in fact, I have worked for several years on correctness arguments for FPGA programming and for GPU programming. So those are notoriously difficult things to get correct, but it's very encouraging to see that the community is embracing these technologies, and hopefully we'll also then go to these correctness by construction approaches. And on that note, I will hand it back to you, Francesco, hopefully on time. And thanks very much to everyone for your attention. I'm happy to take questions offline. Thank you.
Thank you very much, Bruce. Thank you very much, Bruce, for these very interesting insights in things that we should do, but we don't. But we will learn from you. Thank you very much.